welcome Professor Bassam Shakhashiri.
Hello, everyone. Welcome to my lab. Are you ready to learn? Are you ready to have fun? Well, here we go. I promise you a good time, especially if you pay close attention to what goes on. Lots of interesting things are going to happen, some of them very fast. And so I want you to be as attentive as possible, because we are going to do a whole series of experiments, and we're going to obey the safety rules. You notice I have my goggles on, and you also notice that we have a fire extinguisher ready to be used just in case something goes out of control. Experiments that we do in this lab are all exciting experiments. They involve different changes, as we have seen, but they also involve color changes. So I want to show you right over here an experiment whereby we will look at these beakers. And these beakers, there are, see, 1, 2, 3, 4, 5 of them. And what I'm going to do is add clear and colorless liquids to the beakers, and we'll see what happens. So here's the first liquid. You like that? Okay, well, wait till you see the next one. And that's one. And here is the third one. Lots of interesting changes there, right? And let's look at the last one. A lot of interesting, fascinating changes. That's why we do science, to try to understand this beautiful world that we live in and how we can develop a rational explanation for the different systems that we look at. Now, in my lab, across time since I've come to the University of Wisconsin in Madison, I've had the privilege of having many excellent helpers and collaborators, and I've made a lot of good friends over the past 24 years. And I would like for you now to meet one of my very special friends who is about to retire, who has been a part of this program ever since he came to the University of Wisconsin. Would you please welcome Dr. Glenn Doreen. Glenn? Welcome.
Thank you. Thank you. It's been my privilege and pleasure to have worked with this man for more than 20 years. And retiring is a bittersweet pleasure, I guess, because of that. Today I thought I'd bring my chemistry book, and I'd like to read something to you to start this off. That's what you call a hot book. You read any lately? Let's try it again. Now that's a magic trick, and as a magic trick, it still has a fair amount of good science in it. For a fire, you need 3 things, right? You need fuel, oxygen, and a source of heat. And all of those are present in the hot book. If we can look at the hot book, if you look at the bottom of it there, it has a little concealed switch, which I didn't show you, of course. Inside, you have all the ingredients for a fire. We'll hold this up to the camera, and you can look at it on the monitor. There's the fuel is sprinkled up here. The switch controls the electricity to those batteries. And if you watch it carefully as I press the button at the bottom, you'll see a little glow right here in the middle at just before it bursts into flame. Okay, enough of that. Instead of producing a flame, let's use the flame to do something else. And we've got a pop bottle. I said a pop bottle, didn't I? If you're aware, that might be a good idea if you just want to cup your hands over your ears. You'll know where there's something. Yeah, he's already got you trained, hasn't he? Okay, here we go. Now, he said we ought to repeat these experiments. So let's repeat this one in the dark. Are you ready? Here we go. Okay, I think we have a replay of that. Let's try it on the monitor. If you'll examine the monitor, there it is. It's a still frame, actually. It's a still shot. It's not really a replay in that sense, but that's what it looks like for just one very brief period of time. Okay, let's go to something else. The hot book was a magic trick. Let's try another magic trick. I have this magic vessel, which I paid a great price for at a garage sale. And I'm going to pour this liquid into the magic vessel. And we're going to close it up. And then because in order for magic to work, you know, you sometimes have to use a magic wand. So, and in case it didn't get the message, we'll try it again. Okay. Now we're going to pour the liquid back out of here. We're going to pour the liquid back out of here. I said this was a magic vessel. It has the power to turn that liquid into a solid. Now, I don't think we really want to do magic today. We really want to do science. So before I show you what's in that magic vessel, let me just show you a little bit different way of looking at a reaction here. I have a little bit of this white powder, and I'm simply going to pour it into the bottom of this beaker. Okay? I have some more green liquid. It's just water with food coloring in it, just as the other one was too. And what I'm going to do is I'm going to pour these back and forth and mix them. So, you ready? Now you may have some idea of how this works. It's a two-chambered vessel. Maybe we can see that on the, there we go. With the silk in one side, a little bit of that white powder in the other. And that white powder has the ability to gel, to tie up all of that water, all 700 milliliters or so of it, there. It's a very useful substance. Some of you may have used it. You may not have known that you used it. Anybody recognize those? Yeah, super absorbent disposable diapers. Thousands of pounds every year are used for exactly that purpose. Well, with that, let's get on with the show. Again, thank you, Professor Shakhashiri.
Well, thank you very much, Glenn. Thank you. We are going to miss you, Glenn, but you promised to come back not only this time of the year, but any time that you want to. You're most welcome in my lab. And now we're going to move on to a couple of other experiments. And what I have here is a solid, we call it sugar. It came out of this bag, actually. And I have another chemical, which is a liquid. This is sulfuric acid. Sugar is made up of three elements: carbon, hydrogen, and oxygen in combination with each other. It's called a carbohydrate. And sulfuric acid is made up also of three elements: hydrogen, sulfur, and oxygen. Now, sulfuric acid has a great affinity for water. And one of the things that we're going to do with this set of chemicals is to see what happens when we add the sulfuric acid to the sugar that has in it a lot of water. We're going to do this experiment not over here in the middle of the bench, but we're going to do it at this end of the lab, right behind and right inside this plastic box, which is connected to the exhaust system. So, as we watch this reaction, we notice that there was a color change. This is always an indication that a chemical reaction is taking place. And if you watch carefully now, keep an eye on that beaker that is inside that box that is connected to the exhaust area. You will begin to see additional, this looks like it's burned sugar now, right? It was browned first, right? And what we'll begin to see, in addition to what we have seen so far now, you begin to see what looks like steam coming off. It's actually condensed water vapor coming off. And you can see that's actually the water coming off from the dehydration of the sugar. And that column, that black column, is actually carbon. The carbon that's left behind after the sulfuric acid has removed all the water from the sugar and, of course, has destroyed the sugar. It's no longer sugar. It has become carbon. So now I'm going to show you another set of experiments over here where I have a solid. It's a purple solid. It's called potassium permanganate. It's purple, and it's so intense in color that it looks almost black. And I'm going to make an indentation on the very top of the small mound that I made here. And then I'm going to take a liquid called glycerin. And I'm going to put some glycerin in that small little indentation. And as we often do, we watch and see what happens. We're looking for evidence of chemical change, and sometimes the change is instantaneous. Sometimes it takes a little longer for it to happen. So here we see now some smoke, and we see a fire, and it looks like a volcano. This is a reaction between potassium permanganate and glycerin. And this reaction gives off a lot of energy, not only in the form of light, as we saw, but also in the form of heat. In fact, what we're going to do next is use this very same reaction between potassium permanganate and glycerin to trigger another reaction. And this other reaction is going to take place inside these two flower pots that I have prepared earlier. There is a mixture of a chemical we call aluminum powder and another chemical we call iron oxide. And they're mixed intimately with each other. And on the top of that mixture, I have the very same potassium permanganate that's present there. So I'll make the indentation as I did before. And I'm going to take the two flower pots now over to that exhaust box that we have arranged and carry out the reaction right over here. So I'll put the flower pots right in position. I take some of the glycerin and put it in place and step aside. And what we're looking for, once again, is evidence of chemical change, namely that smoke. There's that smoke taking place now. Now get ready to watch this. We're going to do this in the dark pretty soon. This is a very spectacular reaction between aluminum and iron oxide, and it produced aluminum oxide and iron. But the temperature of this reaction was so high that it melted the iron. So let's take a look at this in slow motion and see if we can gain additional information by doing that. Here's the smoke coming off the top from the potassium permanganate reaction with the glycerin. And pretty soon that will initiate the combination of aluminum with iron oxide. And we will see lots of smoke and lots of sparks. And pretty soon, right from the hole in the flower pot, we will see the flow of molten iron. There it is, coming all the way down. And a very dazzling and spectacular reaction. In fact, what I'm going to do now, I'm going to walk over there and I'm going to show you a piece of the molten iron that's down here. It's not molten anymore. It's just, you see, it's still red hot. It was so hot before, it was bright white. And we caught it in a bucket of sand for safety reasons. So this is what the iron looks like that was produced from that highly energetic reaction between aluminum oxide, between aluminum and iron oxide to produce aluminum oxide and iron. Okay, so I'm glad that you are paying close attention to all these different reactions that are taking place, and I'm glad that you like them. So what we're going to do next is look at a reaction in this large beaker over here. This beaker has a volume of 4 liters, and into this beaker I'm going to put, that has water in it. It has a magnet that is sitting on top of the, inside the beaker on top of a stirring motor, and it causes it to spin. What I'm going to do is take a colored liquid, which is a mixture of indicators, and put them right down the middle of the vortex that's being created. And these chemicals, these indicators, have specific colors, which I want to show you now. We can alter if we add an acid. So I'm going to add a drop of an acid, 2 drops of an acid, and you begin to see that the color of the acid-base indicator we're using is changing. So color changes are not only attractive to us, but they are useful to indicate to us that a reaction is taking place. In this case, a reaction between an acid and a base. Now I add a different chemical, in this case a base called sodium hydroxide, add a couple of drops, and let's see if we can bring about a change in that color. And you see pretty colors developing as a result of the presence of a mixture of acids and bases using a combination of indicators that change color as the pH of the solution changes. So another set of pretty colors that we have in my lab.
Stay with us. You won't want to miss the next experiment Professor Shakhashiri does.
This experiment that we're going to do has to do with a form of energy we call sound energy. You know, when I talk, my vocal cords vibrate and push the air and create sound waves that your ear then pick up and you hear me talk. And so what we're going to do is use chemicals to create sound. And the way we're going to do this, well, a couple of different ways. I'm going to take this organ pipe and blow into it. Can you hum that? So that's beautiful. That's the flow of the mixture of nitrogen and oxygen through this pipe. So what I'm going to do next is take some gaseous oxygen out of this tank, and I'm going to blow it in and see what happens. It's about the same pitch, right? Now, the next thing I will do is take a gas which has a smaller mass than oxygen or nitrogen, namely the gas helium. And we'll blow that through and see what happens. You hear the pitch is higher, right? The pitch is higher because the mass of the gas is smaller. So what happens if we take a gas which is heavier than helium and even heavier than oxygen or nitrogen? What would you predict will happen to the pitch? It'll go lower. So let's see if that's true. I have in this cylinder a gas called sulfur hexafluoride. I'm going to, and it is heavier than air, I'm going to fill this balloon with it first. oh, you don't have to cover your ears. It won't. It'll be all right. And I want to show you that it's really a balloon filled with a gas with special properties. See, here's the balloon, has sulfur hexafluoride in it. I let go of it, and it bounces down, just like a basketball, right? That's because the gas is heavier than air. So that's the gas now I'm going to blow into the pipe, into the organ pipe. We'll see what happens. We'll hear what happens. So sound energy then is affected by the mass of the gas that is involved. So let me show you another thing. I'm going to take some of this helium gas and replace the air in my throat with the helium gas. We'll see what happens.
Hello, everybody.
Do you hear a change in my voice? The pitch is much higher because what is inside my voice box is helium, and helium is a gas that has a smaller mass than air. Now that I got my normal voice back, that goes to show you that I really did not inhale. You get it? All right, so we move on and do another experiment. This experiment we're going to do in this round bottom flask. It has some water in it. Actually, I don't need the water, so I'm going to dump the water out. I go over to the sink and I dump the water out. There it goes down the drain. And I will take a liquid, a small amount of a clear and colorless liquid, and I put it inside the flask. And then I take a larger amount of a different liquid, and I put it inside the same flask, and then put the stopper back on, and we see already that we have evidence of a chemical change because the color of the mixture is different than either component was before. So we need to mix those things very, very quickly, and one way of doing that is to simply shake them up like this. And you see what's happening is that we truly have evidence of chemical change, right? Not only is the color changing from the dark that it was, but it is now a nice silvery color. I can see myself here. Can you see yourselves in there too, right? There you go. So let me show you something else that I have here. Look at this one. This was prepared earlier, and now if you drive around town and you see large Christmas ornaments, you know where they came from. So now let me get over to this part of the lab, and I want to show you that I have a clear and colored liquid in my left hand and a clear and colorless liquid in my right hand. And what I'm going to do is mix both of those liquids in this special glass spiral assembly where I have a funnel hooked up to the glass spiral and a receiving flask down here. So we're going to do this with the lights turned off. So let's see what happens when we mix those two liquids together. With the lights off, oh, we go, here we go. Isn't that neat? Okay, with the lights on now, this is an example of what we call a chemiluminescent reaction. This is the release of energy in the form of light, not in the form of heat. Well, I want to thank you for coming to my lab, and no matter what you do, remember when you do experiments to do them safely, and always remember that science is fun. Thank you very much.